Lab 11 Full Counting Mechanism for the Alarm Clock. The goal of this lab exercise is to create a complex multi-digit counter using a sophisticated array of array data type which will count the hours and minutes of the alarm clock. We know that the alarm clock should contain a time count component which will count the 1-minute pulses generated by the pulse gen to generate 4 clock digits that shall be displayed on the LCD display. It should also allow us to change the value of time to a new value. From the block diagram, we see that on every passage of the clock, if load underscore t is high, the time underscore data is loaded with the value of set underscore data, which is given by the time set component in the final alarm clock design. Load underscore t is driven by the FSM controller in the final design. Else, if 1 underscore minute is high, we load the time underscore data with its incremented value. We know that 1 underscore minute pulse is high only for one clock cycle. So when 1 underscore minute is 0, the time underscore data value remains unchanged. On reset, the time underscore data value will be reset to 0. Time underscore data and set underscore data consists of four 4-bit arrays, one 4-bit array for each digit in the alarm clock. This is in the BCD format. The incrementer here operates on all 4 digits, incrementing them in the pattern of a normal 24-hour clock. We know that the clock is represented by 4 decimal digits, where each digit in turn is represented by 4-bit array. Hence, we use array of array data type to represent the hours and minutes of the alarm clock. Here, display underscore t is the data structure, which is an array of arrays. Therefore, display underscore 4 is a 4-element array where each element in turn contains a 4-bit array. The 0th element of display underscore 4 represents the least significant minute digit. Element 1 of display underscore 4 represents the most significant digit of the minute. Element 2 of display underscore 4 represents the least significant hour component, and third element of display underscore 4 represents the most significant hour component. Each of these components is in turn made by 4-bit array. An example 4-bit array and its equivalent decimal value is shown in the table.
The counting algorithm for the time count component is as shown. We know that the time count component must increment in the pattern of a normal 24-hour clock, that is from 0000 to 23:59 and then roll back to 0000, where the 2-minute digits should count up to maximum of 59 and the 2-hour digits to 23. The set of rules defining the behavior of time counting mechanism is as shown. This time count algorithm starts with the exceptional case of 23:59 and ripples from ms hour to ls minute. This need not be the best method for simulation efficiency, as it checks the most common condition last, but it is the easiest to design. You can have your own algorithm to implement the time counting mechanism. We see that when time is 23:59, we set all the components of the clock to 0. Increment ms hour component whenever time is of the form x9:59. Increment ls hour whenever time is of the form xx:59. Increment ls min whenever the time is of the form xxx9. Else increment ls min for all other cases. Let us code the design for the same. The declaration for display underscore 4 is found in the alarm types package in the file p underscore alarm underscore types.vht, and hence we declare this package using the use clause. This type is declared in the package as it will be used by many components in the final alarm clock design. Declare the entity time underscore count along with its port list. We see that the data type for set underscore data and time underscore data is display underscore 4 declared in the alarm types package. We declare a constant 0 for better readability. We know that the VHDL doesn't allow us to read the value of output ports, so we need to declare local signals to implement the counting algorithm and then assign the output ports from these signals. Hence we declare LSmin, MSmin, LSR and MSR. The final output will be the concatenation of these signals, where LSmin represents the least significant minute digit of the clock, MSmin most significant digit of the clock, LSR least significant digit of the clock, and MSR most significant digit of the clock. Next we implement the counting mechanism in the process time underscore counter. We know that the reset is asynchronous here. Hence, it is a part of the process sensitivity list, and also we check for the reset before the clock edge. On reset, we'll assign all the components of the time to 0. We know that the time underscore count component should perform two operations. One is to load the time value with the new current time value given by set underscore data signal, which is the output of time set component. And it should also be able to count the number of 1 minute pulses. Hence, on every rising edge of the clock, we check if load underscore t is high to load the current time with the new current time value. Else, if 1 minute is high, we implement the time counting mechanism. First, we check for the rollover conditions. When the time is 23:59, we set all the components of the time to 0. Else, if the time is of the form x9:59, that is 9:59 or 19:59, we set the lower three components of the time to 0 and increment the ms hour component. Else, if the time is of the form xx59, where xx can take any value between 00 to 22, we increment the ls hour component and set the msmin and lsmin component to 0. Else, if the time is of the form xxx9, we increment the msmin component and set the lsmin to 0. For all other cases, we increment the lsmin component. Finally, we concatenate the ms and ls components to form time underscore data.
Now let us code the test bench. Create a file t underscore time underscore count.vht. Declare the package alarm underscore types to enable the use of enumerated data type display underscore 4. Declare an entity t underscore time count. In the architecture, declare the component time underscore count. We see that the signals set underscore data and time underscore data are of the type display underscore 4. Declare all the local signals required to connect that to the test bench. Instantiate the component. Also generate the clock. Generate the 1 minute pulses equal to twice clock to make the testing quicker. We apply the stimulus in the process stimulus. We cleverly choose the stimulus such that we can observe all the rollover conditions.
We apply the reset for one clock period and then synchronize to positive edge of the clock by waiting for period by 2 and then drive load underscore t high and load 0008 and count to test the rollover happen on ls min digit of the clock. Next we load 58 and count for 5 seconds, that is 10 clock cycles, to watch the rollover happen on the ms minute of the clock. Next we load the set underscore data with 9:58 and count to test the rollover happen on ls hour of the clock by waiting for 10 clock cycles. We also load 11:58 and count to test the midday increment. Finally, we load 23:58 and count to test the midnight increment. Finally, we terminate the simulation. Let us simulate the design by running the xrun command along with the GUI option. Select the top file, add to waveform, press the play icon on the toolbar, adjust the time scale and the zoom option. At 15 nanoseconds, reset is low and hence the value of time underscore data is all zeros. At 25 nanoseconds, load underscore t is driven high and we apply the value of set underscore data to be 8. Hence, time underscore data takes the value 8. We then drive load t to be low to enable the count operation. We see the increment happen and the time rolls over from 09 to 10. This verifies the ls min rollover. Next, to observe the ms min rollover, we drive load underscore t high and apply set underscore data value to be 58. This sets the value of time underscore data to 58. We then drive load underscore t low in order to enable the count operation. We see the count increment from 58 to 59 and then it rolls over to 100. We next verify the ls min rollover. For this we again drive high on load underscore t and apply set underscore data with 9:58 and then wait for 10 clock cycles to observe the increment and rollover happen. We see the time increment from 9:58 to 9:59 and then the rollover happened to 1000. We next verify the midday rollover by driving load t high and applying the value 11:58 on set underscore data. This assigns the value 11:58 to time underscore data and then we drive load underscore t low to enable the count operation. This increments the count to 11:59 and then it rolls over to 12. We shall next verify the midnight rollover. For this we apply load underscore t high and the value of set underscore data to be 23:58 and then we drive load underscore t low to enable the count operation. We see the time underscore data increment to 23:59 and then it rolls over to all zeros. This verifies the counting mechanism of the alarm clock. Let us now synthesize the design. Copy the genus underscore shell.tcl file into the lab area. Set the design variable to time underscore count. Read the file p underscore alarm underscore types.vht along with the design file. Invoke the genus tool by executing the genus command. Observe the netlist generated on the schematic pane. This completes this lab.